Please welcome Pete Bunce.
Thank you very much, Craig. I'm going to talk from down here so you guys can see the slides. We asked the guys to pull the podium down so everybody can see them. I just want to say, you know, having been, I think I'm going into year 16 at Gamma now, I've been able to watch Redbird and migration grow over the years, and what Jerry and Todd and Charlie and Craig have created here for all of us has been so influential for the industry. And I know I speak for, as Craig said, all of our associations are so close, but I know I speak for my good friend Mark Baker and for Jack Pelton to just say this is a tremendous event that we support wholeheartedly, because it really gives us an idea to talk about where our feedstock comes from. Let us talk about issues and be able to help chart our future. So again, thank you to Redbird. What I'm going to talk about today is different kinds of fueling for the future, and we all need to be aware of what's out there. Now, several of us attended Jerry's very provocative brief yesterday on battery technology, which I thought was fascinating, and I'm going to start out right now telling you there's really no more efficient way in the world to be able to get energy than blowing up dinosaurs. I mean, that is the way we do it, okay? But we all have to realize it's a changing world. And very soon, we will not be able to operate airplanes in Scandinavia that burn dinosaurs, that burn fossil fuel. They're just outlawing them. So we, as an industry, have to adapt, and we have to do things to be able to survive. So I'm going to talk about some of that technology, and then I'm going to pass it to my Director of Engineering and Maintenance, actually our VP, who's been doing this long, and he's the really smart guy. And he can dive into any engineering stuff you want to start talking about. So let's go ahead and start. If we look at the different types of fuel that we look toward the future, obviously we're all familiar with jet fuel, but it's changing. We're going to have to start using sustainable aviation fuel, and we're going to have to start using a lot of it. So I'm going to touch on that. Talking about electrics, of course, talking about hydrogen, and then I'm going to pass it off to Walter to do what we all know is the issue du jour right now, which is AvGas and what we're going to do with the lead that's in it. So let's start in talking about electric propulsion. There's two types of aircraft out there that we're really concerned about now that we're trying to get certified. CTOL, conventional takeoff and landing type aircraft, and eVTOL. Some of the eVTOL aircraft, like Joby, if you look at Joby, it's got wheels on it. Why is that? Because they want to use the wing form and the fuselage form to be able to create lift and be able to certify as much as possible under Part 23, because we spent years and years trying to redo that regulation, so it's a more common sense way to use international consensus standards to certify an aircraft. The other thing I want you to look at is look at cockpits that are out there right now. Is that a whole lot different than what you're already used to if you're working with modern type of panel technology that we have? No, it's very easy to adapt. You might have a side stick controller and that, but those that fly Cirruses and other aircraft, Columbias and things like that, people are starting to get used to them, and we know it's very easy to adapt to. So it's not that different. Some of the displays we're working on to make as friendly as possible, but on the electric aircraft themselves, they're very simple to fly. They have a large degree of automation, but there is great variance between them. I've flown the Joby Sim and I've flown the Beta Sim. Huge differences between those aircraft and how you use the automation. So we'll touch on that for a second. These are just Gamma member companies and the different designs that are out there. Now, many of these aircraft in first stage are electric. That'll have very short range, all electric. Most of them will have a hybrid capability with them, and I'll touch on that in a second. But notice that it's a big mix of CTOL and eVTOL. You'll see very shortly in the next few weeks Alice's first flight, which is an Israeli company, Aviation, that's up in Arlington, Washington. And notice Aviation's aircraft down on the second row, second from the left there. It looks like a business jet with two electric motors. 8,000 pounds of batteries and 9 seats, but it just looks like a conventional aircraft. A lot of these companies are trying to get airplanes in the air using current standards, using as much as we can without having to create new things out there that the FAA would have to promulgate, and we know how long that takes. Also note on the chart there, and again, these are just Gamma member companies, but there's some traditional manufacturers that have jumped into this with both feet. You know, Bell is no longer Bell Helicopter. Bell is Bell, and their logo is a dragonfly for a reason. If you look at, if you go ahead and look at Embry Air, their Eve consortium is going to go public in the next few weeks. And it's going public because they see the tremendous potential. And they're end-to-end. They're just not the machine itself. They're talking about the whole air traffic control system that they can sell into the developing world as an entire end-to-end capability to be able to get their eVTOL aircraft up and running. And we all know, any of you who have been down to Sao Paulo, you go ahead and you see how much helicopter traffic is just in that city. It's phenomenal. It's nothing like what we have here in the U.S. So pilot training to this audience becomes very important. So what are we trying to do? Well, right now we're having a big roadblock within the FAA because they created this stupid thing many years ago called powered lift. We, as an industry, protested against it, but the FAA forged forward and created this pathway called powered lift. And right now, the FAA can't get out of its own way. It's bureaucratic paralysis, because flight standards in the FAA does not know, once we certify these aircraft using Part 23 and special conditions, they don't know how to translate that into being able to fly them with operational rules. And it's a big conundrum, and we're having to push this up. In fact, Walter and I are working with the FAA next week to try to unstick this, but for years it's become a real stumbling block. But if you look at what our concept is, at least in the initial phases, is most of these aircraft will be manned. Now, Wisk is an exception. Wisk has a plan to be able to get airborne autonomous to start with, but they're tourist type of trips. They're two people that get in, pilot on the ground, controlling the aircraft, and actually the occupants can't do a whole lot except sit out and look out of the bubble and see this trip. That's what they're starting to do in New Zealand. But when you're talking about paying passengers for transportation, in that virtually all of them will start in the crawl walk phase with a pilot on board. So how are we going to get them qualified? Well, the path is right now going to be standard. They're going to have a PPL, they're going to have a commercial. A lot of them won't be flying instruments to start with because a lot of the aircraft are not going to be instrument capable. We have icing issues and things like that. And in the initial group of aircraft, most of them will be just VFR day only. But they'll have a pilot on board, and it's been fun to watch ALPA, the Airline Pilots Association, come around to originally being skeptical of this industry because they're going, oh my God, it's going to be so autonomous, they're going to get rid of pilots, what are we going to do? To being able to say, well, wait a second, you're going to start off with pilots, that's a feeder for us, we don't have enough pilots, people can get experience as they're working toward their ATP flying eVTOL aircraft, so heck, this might be a good thing, and it's been fun to watch them come around. But right now, we all know that, you know, you can fly a Part 23 jet, you need a type rating. You can fly a Part 23 turboprop and not need a type rating. You may have to have specialized training like in the MU2 or in the R44 and that, but we have different types of training there. We also have endorsements. If we want to go fly tailwheel, we get an endorsement, right? So how are we going to do that? Right now, we're thinking we don't want to call it a type rating, but we'll have an endorsement that's very type specific to the type of eVTOL aircraft you fly. Later on, our future path, once it becomes very highly automated, then we may be able to streamline that whole process itself. But there's still things that we all know that humans can do better than computers. Right now, you know, all of us, when we try to use Siri or any of the other voice technology out there that translates, they can't get it right half the time. There are things that we need humans in the loop for. So this is an ongoing process that we've got with the FAA right now. Also, if you're paying attention, big companies are very serious about what's happening right now. You can produce a tremendous amount of electricity with a spinning turbine. Okay, so now think about hybrid. GE's been one of the pioneers, but Rolls-Royce is with them. Pratt, which is obviously a Raytheon company, they are all very much exploring how much power you can do to augment traditional burning of fossil fuel with other types of electrical motors in that, and especially in the regional airline world, there are some interesting possibilities out there, and that's why you've got Boeing, Airbus, Embraer, all of these companies exploring electric power in that region. So now let's touch on hydrogen. Okay, again, a fossil fuel. Now what I'm talking about though here right now in where we are in technology, we're not talking about burning hydrogen. Hydrogen you can burn, but you've also got to cool it to be able to get it into the combustion chamber to be able to burn it. So that's cryogenic cooling, that's all kinds of technological leaps that we have to have to be able to burn it. And then ultimately when you burn hydrogen, you still have things like NOx, you still create contrails, so you have problems that we're already being challenged with by a lot of environmentalists up there about contrails and everything else. But when you change the thought process in hydrogen, you talk about using gaseous hydrogen and a distribution system that gives you very lightweight containers that you can then adapt into an aircraft and be able then to use a hydrogen fuel cell to be able to produce the electricity you need to drive electric motors. You start to go and start to change the paradigm out there. Now, obviously, do we have a hydrogen infrastructure right now? No. Are there companies out there trying to build it for not only aviation, but so many other purposes in the world? Absolutely. There is a lot of potential there. So I showed you a picture of Desrosier, some of the work that they're doing in the UK, but also in the US, and more companies are looking at hydrogen fuel cell technology, the delivery of hydrogen to be able to power aircraft. So think when somebody talks hydrogen, think of gaseous hydrogen, don't think about burning the liquefied hydrogen for at least this point in time. So the hydrogen fuel cell is just directly in the powertrain. The advantage of an electric motor, we all know, and in fact Jerry and I were talking the other day when Redbird was looking at a diesel motor, the pulse that you get, the actual pulse that you see when you slow that down and look at it under a very quick, a camera that can capture time and watch it very slowly, the pulse that you send up there is pretty dramatic. If you use electric motors, you start to get rid of a lot of that. And electric motors, we all know, you can have a 10,000 hour TBO on an electric motor. So we start to change also the maintenance dynamic when we are able to use electric. So having the hydrogen fuel cell in the powertrain does things like it allows you to reduce some weight coming from carrying a lot of batteries, and there's a lot of potential that we're looking at out there. So now let's switch to Jet A. We all know Jet A is cheaper than AvGas right now. It's very abundant. We know how to produce it, but unfortunately, because, now if you were in a perfect world, people probably look at it, and if it was all clean sheet and you say, who should be blowing up the last set of dinosaurs out there, it's probably aviation, because we've got the tougher challenge to be able to transport people in an aluminum or carbon fiber tube up at very freezing temperatures, high altitude, and we should be the last ones to be able to use it. But that's not how the world is going. Our survival depends on being able to go and find something to help us with jet fuel, and that is sustainable aviation fuel. First of all, and I'm going to say this a couple times, sustainable aviation fuel is jet fuel, okay? Whenever people talk about it and they say SAF, you've got to also put back in your mind, it is jet fuel, because it is, once it's formulated in the different amounts of mixture we're allowed to use with the feedstock that's put in there, it's recertified under ASTM standards to become jet fuel. So we all know the normal path for petroleum. With sustainable aviation fuel, you get credit for how it is grown and all of the cycle that's involved in it, and that's why all the energy of the airlines right now, and you're talking global airlines, business aviation, everybody that's burning turbine fuel is focused on SAF, sustainable aviation fuel. Now, this is a very busy slide, and all I want to do is point out in the different pathways here, look at how many times ASTM is in that process, because it's going to be important when Walter talks in a few minutes about AvGas and our transition here. But what I want to focus on is the lower left-hand corner there, the different pathways. So right now, we have 7 authorized pathways that are out there. Each one of them are a little bit different. So one of the things that we've learned, right now, those of you that have been paying attention to SAF know that we're maxed, or our requirement right now, we can blend no more than 50%. Why is that? Because some of these pathways don't have enough aromatics in it that, and you have to start adding aromatics to be able to make the seals and everything else work on our aircraft. So right now we are limited to 50% blend, but virtually all the engine manufacturers are testing with 100% SAF. But not all these pathways get you an ability to be able to use 100% without augmenting it with those aromatics in that. There are certain pathways that have aromatics in them or specifically put it in. There's also some that are more useful than others. Out of all of these, sugar is probably the least productive. You can only blend up to 10% when you're going and converting sugar into SAF or to the neat additive that you put into it to be able to use it. The rest of them you can go up to about 50%. The other thing is there isn't enough feedstock out there that any one of these will go ahead and do it. We need all the feedstocks going. If you look at, you know, grease, cooking grease, I call it the Willie Nelson formula because Willie has a company that's going and taking cooking grease. Well, who's using most of that? It's the truckers. The biodiesel lobby is using all of that. We have to compete with them to be able to get feedstock for our industry for SAF. So it's a very complex problem. The Biden administration put forward the grand challenge that's really trying to boost the amount of government investment, and it was actually in the Build Back Better plan. We're hoping and we're trying, along with our airline brethren, to break out that piece that was in Build Back Better that supports SAF and the government's investment. One of the biggest things that we want to try to do is have the military use more SAF because they're a huge user. Now, obviously, it's going to cost the military more, so there has to be government subsidization, basically, of the cost of fuel for the military to be able to have them to use it. But we're all in this effort together. It's a global effort to be able to go ahead and try to further develop SAF. Now, we in business aviation, now you're drilling down to general aviation, everybody that uses jet fuel, and that includes those of you that are operating on diesels and everything. We recently at NBAA base last fall made our commitment to 2050 to be able to be net zero in emissions. Now, all of us sitting here in 2022 go, how the heck are we ever going to do that? There's been a lot of work. Well, it's not just SAF. A large part of it is being able to produce smarter and smarter aircraft that are more and more efficient, wing designs, lighter materials, doing some things with engine technology, electric technology, and also we're going to have market-based measures to be able to get there. But if you see in the chart the sand chart we've been using now since 2008, as we revise this, if you look at the wedges that are out there, alternative fuels, which means SAF, is a giant wedge. It's a giant wedge. The only way that aviation is ever going to get to net zero by 50 is with sustainable aviation fuel. You notice that on the out years, the technology piece grows. We were looking at different technologies, when they'll mature, when you're able to certify them and get them working into the system to be able to go and provide for that technology wedge. And I don't want you to, this is just illustrative for you to look at what all of our companies, and that's the great thing. Craig mentioned that how all the GA associations work together. I'm very proud that every single one of the manufacturers, down from all of those electric aircraft that you saw up to all of the jet manufacturers, got together and looked at all the technologies that are out there, and when at best estimate we could actually get it certified, get it into production aircraft, and get it out in the system. And they built this big matrix, and they used all of this to be able to build the technology piece of that sand chart I just showed you to be able to determine what we should be able to do as we go forward. So the challenge is huge for all of us in the environmental arena, but it's exciting. And I still think, now I wasn't old enough to be around during the very dawn of the jet age, but I look at this time in aviation now. We all know how many people are flying, and we all know what's going on out there. The investment that's coming into our industry, this has got to be what the dawn of the jet age was like. This is such an exciting time in aviation, and that's why I'm so proud to be able to work with Mark and Jack and Ed Bolin and NBA and all of this, because it's a great time to be in our industry. So with that, now I'm going to pass on to Walter Desrosier, again, the head of our VP for Engineering and Maintenance. Walter's been working the AvGas issue for many, many years. He's been at Gamma longer than I have, I think over about 20 years now. And he is a superstar engineer, so if you got any really tough questions, we're going to have Walter field them as we go to AvGas. Walt?
All right. Thanks a lot, Pete. So I'm going to talk about AvGas. And so AvGas isn't nearly as exciting as a lot of the futuristic things and the development and the technology that Pete was talking about and how exciting things are that are coming our way in our future products. But it's one of the most critical things facing us today, because today AvGas is supporting our fleet. AvGas is key to general aviation and key to the utility and the viability and the success of the GA transportation system. And I could talk for a long time about all the work that's been done. I can talk about the challenges and the issues that we've had in the past, but what I really want to do is focus forward. Where are we today? What are the things that are facing us, and what are we going to do about it? So everybody here in GA is very familiar with all the headlines and the current news and the information about what's happening at Reed Hillview Airport with Santa Clara County and some of the efforts over there to try to ban leaded avgas from the airport. So what I want to do is highlight this is one of the biggest threats to GA that we have seen in decades. We have talked about avgas for over 20 plus years. We've talked about all the efforts to move to an unleaded avgas. The pendulum has swung depending on how urgent it is to it's less urgent, and the level of effort and investment and activity has gone up and down. But right now we are facing an environment that we see that leaded avgas is going to have some threats in terms of continued availability. Right now, the approach that's been taken in Santa Clara County is they've hired some firms to do some research, put together some reports. Nothing new about tetraethyl lead. We understand it's a toxic chemical. We understand it has health impacts. We understand that GA is actually a very small contributor, but we are now the largest contributor now that it's been eliminated everywhere else. So nobody's defending the use of tetraethyl lead. There's a continued investment and continued effort and goal to get rid of it. But what they've done in Santa Clara County is they've taken all that data, packaged it in a way, and then tied it to some of the issues du jour of today. They've tied it to social injustice. They've tied it to the location of airports and the communities that airports are in, and that there's low-income communities in that area, that there's minority communities in the area, and they're really generating a focus and attention on where things are in terms of the concern about tetraethyl lead. And that's raising the concern to the level that it's going to cause some real challenges in terms of community acceptance, public acceptance, and understanding of GA and understanding of the actual impact that we have from an environmental perspective. Now, this is not limited to Santa Clara County. So just as an example, one of the headlines in Southern California, on the other side of the state, they've already started taking this approach that Santa Clara has used that report that was developed by some law firms, which are now being sent to all the communities across the country as a pathway of how they can attack that airport, how they can attack GA, and they can use this as a boilerplate on how to do that. Now, there's also activity at the federal level. So the EPA has been looking at doing an endangerment finding, which is their process under the Clean Air Act of how you regulate certain toxic substances. And so they've been looking at tetraethyl lead for many, many years, and they've had some initiatives already started and underway. But just in October, there was a petition filed by several environmental organizations, but not just environmental organizations. You've got Alaska Community on there. You've got the County of Santa Clara. You've got Montgomery Gibbs in Southern California. You've got Oregon, an environmental group out there. And you've got the town of Middleton, Wisconsin. They were all signatories on this petition to the EPA, advocating and stating that they are not following through with their obligation to promulgate the endangerment finding for lead emissions from general aviation airplanes. And so in response to that, the EPA responded to that petition in January of 2022. Now, in government process, that is record time. They broke records in how quickly they turned that around and responded. Now, big part of that is all the work had already been done. They've been working on this endangerment finding for many, many years. They've already collected all the data. They've had monitors at GA airports several years ago. They've collected all that information. The notice of proposed rulemaking to propose the endangerment had already been ready to issue, and so they were able to respond quickly. But in that response, they also put out a press release. And in the press release, they said that they will be issuing the notice of proposed endangerment this year in 2022, and that they will plan to issue the final finding in 2023. So that is also a very fast pace when it comes to rulemaking. Now, it's not limited to the United States in terms of some of the regulatory actions. So in Europe, the European Commission has passed some regulations last year in 2021 that is also going to look to start to regulate and have licensing requirements for the use of tetraethyl lead in Europe. And so that has a huge impact on our fuel producers and AvGas producers, both in Europe, but also the ability to import into Europe. But more importantly, Innospec is the one manufacturer in the world, the single supplier of tetraethyl lead in the world. All the tetraethyl lead that we have for our AvGas comes from Innospec, based in the UK. Now, Brexit might actually be something that's beneficial for us here. Brexit means that the UK is not directly under the European Commission regulations. They get to consider it and adopt it in the UK independent of what the Commission does. But the momentum is there in terms of the environmental approach in Europe, and the momentum is there in terms of the regulatory action to take a look at how and when do we phase out the use of lead in AvGas. So in terms of what have been the biggest key challenges in identifying a transition to an unleaded fuel for aviation. So first and foremost is safety. The purpose of tetraethyl lead in our fuel is to boost the octane up to 100 plus. Octane is a measurement of protection against detonation. Detonation is damaging and harmful and catastrophic for engines if it gets out of control. And so that's what the octane is a measurement of, protection against detonation. And so in our fleet, not all GA airplanes need a 100 octane fuel. We acknowledge that, we recognize that. Right now the chart shows, and this is based on engine type certificate data, that the engines are capable of operating safely on a lower octane fuel. So a UL91, UL94 are current fuels that have a fuel specification available. They're not necessarily produced or available at all airports. There's some out there, but the engines are capable of a lower octane fuel on about 67% of the current fleet of aircraft. From a safety perspective, however, about 33% of our current fleet of aircraft require higher octane than 9194. Now, I'm going to say it requires 100 low lead because that's the fuel that's available today. Could it be a little bit less? Don't know. We haven't done that testing, but it cannot go to 9194. Now, the bigger challenge we have in that is our fleet composition. Our fleet, the good news is GA airplanes keep flying. The bad news is GA airplanes keep flying. This composition doesn't go away. So if we look back at how we transitioned away to an unleaded fuel in the automotive industry, first, they identified an unleaded fuel that was a replacement. They had a 10-year transition. You all remember when we had dual fuel. We had a 10-year transition. Basically, the cars that required higher octane protection because of the technologies in those cars at the time, 10 years, they basically phased out, banned leaded fuel. The whole fleet went over to an unleaded AvGas, or an unleaded automotive gas. So in GA, that transition option is not available to us. We need to support and maintain the support for that portion of the fleet because it continues to fly and operate. Now, more importantly, in terms of our infrastructure, our airports, our FBOs, pilots, maintenance, support, services, parts, one of the bigger challenges we have is recognizing that we call it the 70-30. I said about 70% of the fleet can operate on a lower octane fuel, and about 30% of the fleet requires the high octane, high performance fuel. However, in terms of use, the operations in hours or in consumption in AvGas, because these are the bigger, higher performance, higher horsepower airplane engines, also multi-engines, many of them, consume approximately 70% of the AvGas. And so from that perspective, that's a huge, huge consideration on what is a safe and viable transition for us in general aviation. If that portion of the fleet is 70% of the fuel consumed, a higher portion of the hours, a lot of it in commercial service, we got to ensure that whatever transition we identify is going to be safe and accommodate that portion of the fleet. So in terms of the biggest issue that we're facing, Pete had talked about SAF. SAF is Jet A. Basically, it's drop-in. So if you ever heard that term, drop-in, that means we're focusing on the fuel, and the characteristics and the performance of the fuel become equivalent to what the system has already been designed, certified, and operating as safe. It's real easy to move that into the system. In AvGas, when we talk about UL91, UL94, for example, that's basically 100 low lead without the lead added. And so the composition is known, the components are known, the distribution system and the compatibility of that is known. That's essentially drop-in. It's not quite drop-in because we still have to do a placard and things on the wing and in the flight manual, but it's essentially drop-in. And so we're only focusing on the fuel performance, the fuel specifications, and if we identify that, that can be acceptable for use. That's a manageable set of unknowns and challenges to be able to address. However, when it comes to 100 octane, we have not found that. I can go back and talk about 20 years of research and 20 years of effort to find other additives to get to 100, but we haven't found the silver bullet. So a drop-in is not available. So what we're looking at is an approach where it's not a drop-in. So the key to that is it's not just the fuel performance we're looking at. It's not just the aircraft and the engine and the safety of our products that we're looking at. We now have to look at operations impact in terms of aircraft performance, flight performance, runway performance. We have to look at fuel production, fuel distribution, FBOs and where that is dispensed and used. So it's a much bigger set of unknowns. And the bigger challenge to that is it requires, from an aircraft perspective, it requires FAA certification and approval at both the make model engine level and the make model airplane level, because you have to evaluate safety of all the performance areas of materials compatibility and all those other unknowns. But it's not limited to us in aviation. We're very familiar with FAA certification in aviation, but the fuel producers need to do the similar approach in terms of looking at what they need to ensure the safety and compatibility with the production system, to ensure the safety and compatibility with the distribution system, with our airport FBOs. So when we talk about materials compatibility, we focus on the engine and the airplane because we're looking at it from that perspective. But when we're talking about a potential fuel that is completely different, meaning it has different additives that we've never used before, new kinds of chemicals that are exotic and different, we've just never used them. We don't have experience. That all has to be evaluated by all these stakeholders. Or we have a different fuel composition. So instead of, mostly a petroleum-based fuel with 20% of other components added to it, what if it were 60 and 70% other components, chemicals, and only 20 and 30% petroleum? That's a big difference. That has to be evaluated throughout that entire supply chain. So what have we done and where are we today? So I'm going to talk a little bit about the Piston Aviation Fuels Initiative. It's the name of the program. It's a collaborative government industry program or initiative working together. It was established and developed as a result of a recommendation made by an Unleaded AvGas Transition Aviation Rulemaking Committee, UATR. So government speak, but what it did is it brought together all the stakeholders from the industry of manufacturers, from the fuel producers, fuel distributors, operators, government, both EPA and FAA, were brought together in an advisory committee role to look at all these challenges, to look at the current state and make recommendations of how do we get over that, how do we start looking at identifying a high octane, 100 octane replacement fuel for leaded AvGas. And what we developed was a recommendation for a program, which is a collaborative program we call PAFI. But basically what it does is the biggest challenge to fuels being developed and being brought to be available for us was no path to market. Producers weren't investing in the development of a fuel because how do you get it to market? If it requires all this certification, if it requires all this assessment by all these stakeholders, there's an unknown way to get to that market. So we weren't seeing a lot of investment in research and development in developing the fuels. And so this provided a path. So basically the program would bring in fuels, assess the fuels, do phase 1 testing, which is fuel testing, do phase 2 testing, which is equipment testing, engines and airplane. And then that would provide a path to market. So the primary goal and objective of the program was to provide the fuel qualification and testing, and it was going to support 2 primary purposes. One was FAA approval, a fleet authorization approach, an efficient way to assess the entire fleet. Which ones are safe to operate on this particular fuel? Does it meet the needs? And support the ability for the FAA to issue an approval. The second was, in order to commercialize the fuel for production and distribution, we need to have an industry consensus production specification. So Pete mentioned ASTM. So ASTM is the international standards organization that does specifications for all fuels, automotive fuels, diesel fuels, jet fuels, aviation fuels. All fuels are done through that consensus process. But the importance of that is you have all the experts and the stakeholders from across those different groups providing input in terms of, does the fuel fit for purpose? Does it fit not only from the aviation safety perspective, but production, distribution, and then how they would manage and control that in commercial transaction to get the support and buy-in. So one of the key things is we need support and buy-in from all those stakeholders. We need it from the manufacturers because we want to be able to use the fuel in our products. We want the manufacturers to be able to incorporate it into future production. We want the manufacturers to be able to honor and recognize warranty for anybody who might switch fuels. They can do that with the knowledge and understanding of the fuel. They can do that with understanding that their considerations were made. So how did we bring those stakeholders together to make sure all those considerations were made for all those different stakeholders? Under PAFI, they had a technical advisory committee, which included the experts from those different stakeholders. Those experts from engine and aircraft OEMs, operator groups, fuel producers, distributors, FBOs, they identified and developed what is the method and approach that we would do to evaluate these fuels. They came up with a very comprehensive matrix of looking at if we were to do a fleet approach to evaluating safety, but also include in those test methods what would be needed on the producer side, the distributor side. So for example, the materials compatibility testing list. It's not just a list of materials in aircraft and engines, it's a list of materials that were important to producers, distributors, FBOs in terms of tanks and trucks and everything else in the distribution stream. So they came up with a very large, very comprehensive, very complex matrix. Now, not every fuel needs to go through all this. It all depends on the properties of the fuel. Depending on the fuel, if certain areas needed to be evaluated, they would pick and choose from this chart of all the different tests and areas to assess the safety, quality, and performance of a fuel, what would be appropriate to move that fuel through the process. But the important part here is these are consensus, not only tests, but the test methods, the test plans, how to approach it, consensus of all those stakeholders, and they don't address just the FAA certification piece of it. It's not just a Part 23 airplane airworthiness safety. It's not just a Part 33 engine safety for certification. It also takes a look at what does it take to meet the business needs and the risks and the investment of all the stakeholders, from manufacturers to producers to distributors. So where is PAFI today? So initially, PAFI was set up to basically be an awards type of program, a contract award. We set up the program, the government put out a solicitation for all good candidates, whoever, whatever producer, we're going to provide a path to market. And it'll be fully funded with government funding. And fuels come in, they go through the process, they get tested, and they would down select based on the quality and the performance of the fuel. So that was initially how it was set up. 17 candidate fuels came in. 4 advanced to phase 1, which is the first set of testing, laboratory testing. 2 advanced to phase 2, which is aircraft engine and aircraft testing. Issues were identified with all of them. So we learned a lot. So what did PAFI produce? PAFI produced all the test methods and protocols that are necessary to evaluate a fuel to get broad stakeholder buy-in. It also identified a lot of lessons learned that came in. So where are we today with that program? So today the program has shifted. It's moved and said, okay, we want to bring in all high octane candidate fuels and start evaluating and considering them. Not just an award, which was the initial program, but it has moved on to the next generation, which is any fuel. Now, it's no longer fully government funded. It's got a stakeholder involvement in terms of joint funding. There's pre-qualification testing requirements established and defined for the fuel producers or developers to enter into the program. Right now, there's 2 candidate fuels going through that testing. The focus here is still 100 octane replacement. So we're looking for the 100 octane replacement that would be the best fit for the entire fleet. So where are we today? Today, Congress had asked the National Academy of Science to do a report to take a look at where we are with our transition to an unleaded fuel. And in that report, it recommended, in 2021, it recommended we got to not focus just on the one silver bullet, the 100 octane replacement. We got to start looking at a program that defines a path to get to an unleaded fuel by a certain date. So it recommends a multifaceted approach. Reduce lead emissions in the near term, eliminate lead emissions on some kind of path and plan. So perfect is the enemy of the good. That's basically the summary of the report. That's what the report says. And it recommends all kinds of other things that we could do in the interim to try to reduce lead emissions. But one of the key things is it does recommend setting a date for an unleaded mandate. The date should recognize new production cut-in, new engines and airplanes, so we don't keep producing and contributing to the challenge of the fleet. And 2, we need to look at R&D in the event that we need to consider a lower octane fuel than 100. So in terms of the endangerment finding, the EPA has a process under the Clean Air Act. The endangerment finding, they said they're going to publish an NPA this year in 2022. They're going to publish a final decision in 2023. We know the result of that. The decision is going to be lead is toxic, lead is harmful. You have to regulate it, and they have to start looking at how to ban it. We understand that. So, but that's one part of the process. The Clean Air Act establishes a timeline. And under the Clean Air Act, it requires that once EPA does a positive endangerment finding, number one, that's 2023, next, EPA has to set an emission standard, just like they do today for CO2, just like they do today for NOx. They have to set an emission standard. Once the EPA does that, the Clean Air Act is very clear that the responsibility to implement that standard, to make the mandate, is on the FAA to consider safety. So the FAA has to take that standard and figure out the best way to implement that. So that's when we talk about a transition. That's the point in time that they'll look at what's available, what are the options, and what should that timeline be that's appropriate. And so these are just estimates, 2024, 25 for that EPA setting a standard. I think the standard's going to be pretty easy. They're going to say you should not have any lead emissions. So then the question is, what's the appropriate transition date for the FAA to set? Now, the FAA has two parts to that. One is setting the standard for new engine production or certification and design. The next one is how do they retroactively put it into the fleet? That's never been used before. This authorization to regulate fuel composition has never been used by the FAA before. But it's in the Clean Air Act. That is one way they could do it. So where are we today? So I've got all the GA associations here listed. Pete talked about the partnership that we have with all the other GA associations. There is definitely a need for us to come together to protect GA in light of all the activity that's happening right now. And so when we talk about fueling the future, we talk about putting together a collaborative FAA industry initiative. We've had some in the past, but this one's really got to focus on really achieving some key objectives. We need to have urgency and priority towards a solution. I talked about the pendulum swinging. There's been a lot of urgency and priority in some investment, then it's slowed down. We need urgency and priority today to be able to respond to the threats that we see on continued availability of 100 low lead. We need to be able to have chart our own roadmap, chart our path. There's going to be rulemaking to start setting dates and mandates. We can set what we think those right dates are, what that path would be, but we need to have an initiative to take a look at the best way to do that. Protect continued availability of 100 low lead in our infrastructure at our airports today. That's the biggest threat we face. We need to protect that. That's got to be part of this. And then minimize the impact. Whatever the solution is, minimize that impact. So AOPA has taken a lead for the coalition in really trying to do some advocacy, create awareness, create understanding. And so there's a web page specifically on getting the lead out. And that's going to be a source and a resource for all of us in terms of the latest information, the latest updates as they progress. As this initiative is coming together, where are we with fuels today? So there's a lot of work here. There's a lot of hope. UL 100 candidates. These are candidates at 100 octane. The Afton Chemical Phillips 66 partnership, Lyondell VP Racing Fuels partnership, those are the two that are in the PAFI program being tested under the collaborative initiative right now. GAMI just got an STC last year for a 100 octane fuel. It's only on smaller engines and smaller, lower compression engines, but they're working toward expanding the STC. Swift says that they're working on an STC for 100 octane fuel. Shell Aviation used to be in PAFI. They have 100 octane fuel. They had slowed down their R&D investment until they saw a better path to market, but there's an opportunity there. So there's a lot of work being done on 100 octane fuels. But those are big challenges to assess and evaluate those fuels and figure out whether or not they're going to be viable to not only replace 100 low lead, but to be able to be economically viable and available in the system. What are the alternatives in case that doesn't work? So we're looking at understanding where we would be. UL 9194 is a fuel specification available today. It is not a viable replacement for 100 low lead. I talked about the size of the fleet, the composition of the fleet. That lower octane fuel would not be viable. So because of that, one of the other things that we think an initiative needs to focus on is we need to look at the potential of much higher octane unleaded fuels, but maybe not quite 100. And we know these can be produced today. Some of the fuel producers have said their 100 low lead without lead, if they use high quality alkylate, if they use their high quality streams, can achieve a 96, 97, 98. I don't know the final numbers because they need some margin for production and distribution, but that's an initiative that could be looked at in the event we're looking at the 100 octane not being available. So when we talk about fueling the future, one of the things I wanted to leave you with is, you know, as flight schools in training the new people coming into the industry, that's really fueling our future in GA. And so one of the things that you can do is to ensure that there's understanding and awareness out there in terms of what is the real situation with AvGas. Yes, it's a threat, but it's something that's being worked, something that's being addressed. We have paths to look at it, and be informed, sign up on the AOPA website to get information on the latest information. So with that, open it up for questions.
Mark, you want to come on up here too? Get my buddy up here in case there's other tough one right here.
Hello. Okay. I agree with the fuel part of it. My question is this. The aircraft manufacturers for general aviation, like Lycoming, Continental, and so forth, where are they on this, and how much would it cost to change out an engine into, you know, I know Rotex, an Austrian company, they're currently not using 100 low lead. You can use auto fuel in there. So the technology's there. I just think there's resistance from Lycoming and Continental. What's their position on this?
We're in very close contact. Lycoming, Continental are Gamma members. They're very much supportive of trying to be able to move beyond where we are now. But we all know we're flying on 1940s technology. Right. You know, in the automotive industry, they have FADEX, they have electronic ignition, they have all the things that we don't have. What is one of the problems? Is the bar for FAA certification. It's cost, but also we have new methodology out there with which we can test. So there are ways we can detect detonation, you know, that knocking in the cylinders that we didn't have back when originally these aircraft were certified. But they have to have access through whatever programs we create to these fuels to be able to do their testing to see if it meets their certification margins, because liability, we all know, is the giant out there. If they all of a sudden start burning this fuel and an engine goes and the heat propagation and everything destroys that engine, they're going to be the ones that have to go to court, not that fuel supplier, especially as you go downstream. Anything you want to add?
And I would say you know, there's a lot of options for a lower performance type engine, and there's other engine technologies out there. But I think, you know, the real focus in terms of coming through with overcoming this challenge is what are the means by which we can get a high performance engine. These are the high compression, big bore, turbocharged engines. How can we produce that much power on an unleaded fuel?
Yeah, one of the things that we've been really concerned about with you know, the legacy fleet that we have out there is there's a lot of old airplanes. You know, the average airplane out there in the Piston fleet is 46 years old, and that's a large majority of these things. And retrofit scares a lot of members of AOPA in terms of the cost and what it would cost to update those older airplanes. And while we live on electronic ignition in automotive, and you know, we run with liquid cooled engines and it can produce a lot of horsepower, we ask a lot out of a 1940s design. High altitude, hot starts, all those kind of things. And to date, there hasn't been a suitable replacement to do that, or a low-cost way of upgrading those electronic ignitions.
So one of the real opportunities here is we're focused on low lead or 100 octane replacement, but the 96, 97, 98 also, we believe, will go a long, long ways to address most of the existing fleet. And then the challenge of identifying what's remaining and how do we address that is a much smaller, manageable set.
First off, thanks to you and all the other lettered organizations that are working this problem for us. It's a tremendously complex problem with a lot of facets and considerations, and thank you all for the work that you're doing in pushing this forward. As flight school owners, what do you see as the first thing that's going to start to rock our world? Is it going to be increased prices for the fuel for the 100 low lead that we're buying right now? Is it going to be availability of 100 low lead trailing off? Is it going to be other fuels? Now we've got a choice of fuels possibly for a while. What's the first thing that you think that we're going to see that's going to rock our world?
Well, Bobby, you can see out there in California, they're focusing, you know, Swiss strategy has been, we can deliver you fuel out there to flight schools, and since you're flying the most sorties at the airport, we're going to try to take care of that problem. One of the things that we're all very concerned about is what happens with that owner of a Cirrus or somebody else going out there and saying, well, this 94 is fine, I'll just put it in there because I only need a little to get to where I'm going, and then you can see where that's going. But for flight schools, what really concentrating on is, let's say that we get to some of those exotic fuels with those other chemicals, and all of a sudden now refiners have to store chemicals where they didn't before. Does that raise the cost that it's unmanageable? Then we all know distribution. If it's a small company that's trying to produce and they can only produce in one part of the country, the price, if they produce it out west, the price for you on the East Coast is going to be astronomical. Not all refiners can produce the same type of fuel. We all see, I heard from a buddy of mine out in Pierce, South Dakota, his fuel prices that he's offering right there at his FBO are going up 2 cents a day over the last 2 months. 2 cents a day for AvGas. It's going up. So we're just seeing it without, and that has nothing to do with what we're talking about. That's just market forces right now, barrel of fuel. So I can't predict the future, but what we're trying to do is really look, we could price ourselves out of business if we don't do this very carefully.
Yeah, that's right, Pete. But I think one of the things that we do together as an airport community is, commit that we are going to change, educate people that need to understand, the fear of falling lead through the sky. Many of us have lived through this for a really long time. I'd rather have their cards when in terms of call to urgency as ours. But the reality is, most low lead fuels today is 1 gram or 2 grams per gallon in fuel. And when we talk about why we're not too excited about very low lead, that's one of the things I've always had a big hang up about, is that there are some refineries that can't make very low lead. And it's almost like saying, to the EPA, it's kind of okay. And I don't think that's a good place for us to be. But I think as an industry, if we say, hey, we're committed to change, most communities will move on and say, okay, it's going to change out over the next number of years. We'll hopefully get that agreement not too far away. But I think that's the first thing we can do is educate them that we're going to make the change. And that reminding people it's 1 or 2 grams per gallon that are out there today. And it is not something we're proud of, but we want to move away from it. But it is acceptable at this stage.
We're going to go as long as the Redbird staff lets us go. Josh, you're saying
1
one
minute.
more question? Okay.
My understanding was that the lead is not just to increase the octane as well, but to increase lubrication in the engines. How we tested what the longevity of an engine has been with time using unleaded fuel. Are TBOs going to come down to 1,000 hours? Has that been looked at?
So we know historically when we went from 100, 130 down to 100 low lead, we saw some of that. So we had a lot of experience. So most of the components necessary from a lubrication standpoint have been addressed in a majority of the fleet, but we still have a very large, legacy or antique fleet out there. So that continues to be a potential area of impact. That'll be part of the assessment and the evaluation of what is the lubricity of whatever the replacements are. As we go to more of a chemical-based fuel, some of these candidates are more chemical-based, less petroleum-based. That's a bigger issue. Just removing the lead alone isn't nearly as big of a potential impact on lubricity as it is moving to a different composition of fuel. So all of that is part of those testing and assessment. And well, in most cases, it's cleaner or it's different, but we have to know what different means.
Well, I just say we're all, Mark and I are going to be around tonight, and so please feel free. I know this is really a consuming issue for our industry. Just rest assured how, we're close friends. We're virtually on the phone about this issue every day, along with Jack Pelton and Ed and Tim and NATA and Jim Viola at HAI. So we're working it hard, and we've got very good, I criticize the FAA on some of the things on CERT early in my brief, but on this issue, FAA are our friends, and they're working with us closely toward a path forward that's not going to cripple the fleet. Thanks.
Thank you very much.